Before every star, every galaxy, and every second you have ever lived, there was a moment when time itself ignited. Today, we journey back to that first instant where time was born and the mystery of the Big Bang began. If you enjoyed this video, please don't forget to like it and subscribe to our channel. That way you won't miss our future content. The present-day universe stretches in all directions as a vast, almost unfathomable structure, but buried in its light and in its darkness are quiet hints of an origin. Galaxies recede from one another, their spectra reddened, as if the fabric of space itself were being drawn out. A thin bath of microwave radiation pervades everything, arriving from every part of the sky with nearly the same temperature, as though the cosmos still carried the afterglow of a time when it was incandescent. The abundance of hydrogen, helium, and traces of other light elements follows a pattern that could only have been forged in a furnace far more uniform and more extreme than any star. These are not random facts. Together, they form a subtle testimony the universe remembers its own birth. To look outward is, in a sense, to look backward. Light takes time to travel, so distant galaxies appear as they were when the universe was younger. Each faint smear of brightness is a messenger from an earlier page in a cosmic record. Yet, as those messages are collected and interpreted, a profound implication emerges. The universe not only expands, its history can, in principle, be traced back to a state of extraordinary density and heat. As that limit is approached, the ordinary understanding of time begins to lose its clarity. Time is no longer just a backdrop for events, it becomes part of the question itself. In everyday life, time seems simple. Clocks tick, days pass, memories arrange themselves along a line stretching from unknown past to an unknown future. In cosmology, this line is extended dramatically. The current age of the universe is estimated at billions of years, and the story of structure formation unfolds across those epochs with a majestic, if intimidating, order. Stars ignite, galaxies assemble, clusters form, and filaments stretch between them. But behind this orderly narrative lies a deeper mystery. There appears to have been a beginning to this ordered flow, a point at which the very concept of earlier may break down. The Big Bang, as it is popularly named, is often imagined as an explosion that took place somewhere in pre-existing emptiness. Yet this picture misleads more than it illuminates. The Big Bang is not an explosion in space, it is an expansion of space. Every region of the observable universe was once compressed, at least in the mathematical description, into a much smaller volume. The notion of a location where it all began is replaced by a more unsettling conclusion: everywhere began at once. Every point in today's cosmic landscape shares in that origin. If there was such a beginning, then time itself, at least as it is currently understood, must have arisen with it. Asking what happened before the Big Bang may be as ill-posed as asking what lies north of the North Pole. The geometry and laws that define temporal relationships are tied to the structure of space-time, and if space-time itself comes into being, then the notion of before it can evaporate. This is not an evasion, but a recognition that the framework in which questions are phrased may not extend indefinitely. Still, the universe has left clues about how time behaves near its birth. The distribution of galaxies shows that the cosmos has been expanding for billions of years. The cosmic microwave background, nearly uniform but mottled with tiny temperature variations, indicates that the early universe was hot, dense, and remarkably smooth, yet not perfectly so. Those small departures from perfect uniformity would later grow into the vast cosmic web of clusters and voids. The light element abundances reveal that, within minutes after its hot beginning, the universe had cooled enough to allow protons and neutrons to combine into nuclei, locking in ratios that are still measured today. These observables form a coherent story, but they also raise deeper questions. Why did the universe begin in such a low entropy state that time could acquire a clear direction? Why was it so uniform on large scales, yet seeded with exactly the right amount of irregularity to form galaxies and stars? And, above all, in what sense can one say that time has a birthday, a moment at which it emerged from a more primitive or qualitatively different regime? The screenplay that follows does not seek to anthropomorphize these questions with spoken lines or staged exchanges. Instead, it moves in a continuous stream, following the logic of evidence and theory as they converge on the edge of the knowable. The universe is treated as both setting and protagonist, its structures and relics cast not as anonymous scenery but as witnesses. Through them, the story of where time was born begins to take form not as a single, simple answer, but as a layered, evolving understanding of what beginning and time might truly mean. To approach the moment of origin, it is natural to start from what is seen today in conceptually reversed flow. Observations show that galaxies, on the whole, are moving away from one another, with their recession speeds increasing with distance. This empirical relationship, encapsulated in a simple proportional law, reveals that space itself is stretching. The farther a galaxy lies, the more its light is redshifted, its wavelengths lengthened by the intervening expansion. Imagine now a mental exercise: take the observed expansion and run it backward. The vast filaments of galaxies shrink, clusters draw closer, and the distances between galaxies steadily decrease. The cosmic microwave background, already present as a pervasive glow, increases in temperature as the universe contracts in thought. Structures that are now hundreds of millions of light years apart were once compressed into smaller volumes, immersed in a hotter, denser medium. The further this reversal proceeds, the more extreme the conditions become, until ordinary descriptions fail. General relativity provides the mathematical framework for this extrapolation. When combined with the assumption that, on large scales, the universe is homogeneous and isotropic, it yields equations that relate the scale factor of the universe to its energy content. Matter, radiation, and dark energy each influence how the scale factor evolves. Run forward, the equations describe how a hot, dense early state cools and expands into the structured cosmos seen today. Run backward, they converge on a point where the scale factor appears to shrink to zero and densities diverge. This mathematical divergence is what is often labeled as the Big Bang singularity. It marks a limit to the classical description, not necessarily a literal point of infinite density in reality. Nevertheless, it signifies that tracing the same physical laws indefinitely into the past leads to a point where those laws cease to provide meaningful answers. At this limit, time, as defined by those laws and that geometry, reaches an endpoint. There is no early time in the classical model, the timeline simply terminates. The recognition of a beginning was not immediate in the history of cosmology. Alternative models once sought to avoid an origin in time, proposing steady-state universes or cyclic expansions and contractions that repeated without a true starting point. Over decades, the accumulation of data, the discovery of the cosmic microwave background, the detailed mapping of its fluctuations, and the measured abundances of light elements favored a universe with a hot, dense early phase that could not be indefinitely extended backward without encountering radically different physics. Yet even as an origin came to be widely accepted, misunderstandings flourished. The Big Bang became, in popular imagination, a kind of firecracker exploding into pre-existing emptiness at a particular location. This mental picture places the event in a larger arena than the science at a center, neither of which the theory supports. Instead, the expansion is everywhere at once. There is no edge to the universe from which matter is fleeing, no central point where the explosion occurred. The fabric of space-time itself is stretching, and every moving observer sees other distant observers receding. In this context, time is measured along world lines that are tied to the average motion of matter. The cosmic clock is defined by the age since the hot, dense phase began to expand and cool. For each galaxy following the general flow, this clock yields the same value, up to small corrections due to local motions and gravitational fields. When cosmologists speak of the age of the universe, they refer to this shared measure. It is a time coordinate anchored in the global expansion, not in local, arbitrary choices. Rewinding the expansion, then, is not a literary flourish but a precise conceptual operation within the theory. It reveals a past in which density and temperature increase without bound as one approaches a finite proper time in the past. At that boundary, classical spacetime ceases to be a reliable stage. The geometry that once defined time now dissolves into a regime where quantum effects must dominate. In that regime, the very questions about before and after may need to be reformulated. This realization shifts the central mystery. It is no longer solely about what the universe looked like at extremely high temperature and density. It is about the status of time itself. Does time extend beyond the classical boundary in some more general theory, or does the notion of temporal sequence arise only after certain conditions are met? Is the Big Bang a literal beginning, or is it a transition from one description to another, from a pre-geometric or differently structured reality into the familiar space-time continuum? Rewinding the cosmic expansion thus acts as a conceptual lens, focusing attention on a narrow interval near what appears to be the origin. In that interval, the clues carried by light, matter, and geometry converge to a point of ambiguity. The known laws of physics, so successful at describing everything from planetary orbits to the life cycles of stars, admit their own limitations. Time, which seemed to flow smoothly all the way down, now appears to meet an edge where it must either transform or give way to a deeper description. The phrase Big Bang conjures images of a concentrated object blasting debris into emptiness. In reality, no such center surrounding void exists in the standard cosmological picture. Instead, the early universe is better described as a nearly uniform fireball, a hot, dense state that fills all of space. Every point participates in the expansion. There is no external theater in which the event plays out. In this primordial fireball, matter and radiation coexist in a tightly coupled state. Photons scatter frequently off charged particles, constantly exchanging energy and blurring any attempt to speak of distinct beams of light. Electrons, protons, and neutrons form a plasma that behaves collectively. The temperature is so high that atomic nuclei can be broken apart by energetic collisions, yet as the universe expands, it cools, and a sequence of thresholds is crossed in rapid succession. During the first fractions of a second, processes occur at energies far beyond those accessible on Earth. Particle-antiparticle pairs of many varieties form and annihilate in a seething equilibrium. As temperatures fall, subspecies drop out of equilibrium, their abundance is freezing in as relics. Baryogenesis, the process by which a slight excess of matter over antimatter emerges, leaves behind a net matter content that will eventually assemble into stars and galaxies. Though the detailed mechanism remains uncertain, the fact of this asymmetry is crucial. Without it, matter and antimatter would have annihilated almost completely, leaving a universe filled with little more than radiation. As expansion continues and temperatures drop to levels comparable to those in nuclear interiors, protons and neutrons begin to fuse. In a brief era known as primordial nucleosynthesis, light elements are forged, hydrogen remains dominant, helium-4 becomes a substantial minority, and trace amounts of deuterium, helium-3, and lithium-7 are produced. The relative abundances of these nuclei depend sensitively on the density of baryons and the expansion rate at that time. Billions of years later, measurements of these abundances in ancient gas clouds and old stars serve as checks on the theory, confirming that a hot, dense early phase left its chemical signature across the cosmos. For hundreds of thousands of years afterward, the universe remains opaque. Electrons are still free, and photons cannot travel far without scattering. Fireball cools, but light remains trapped in a fog of charged particles. During this time, density fluctuations, tiny variations in the primordial plasma begin to grow under gravity's pull, while radiation pressure resists collapse. Waves of compression and rarefaction ripple through the plasma, setting up acoustic oscillations whose imprints will later be visible in the pattern of temperature variations in the cosmic microwave background. Eventually, a critical threshold is reached. The temperature falls low enough for electrons to bind with nuclei, forming neutral atoms in a process called recombination. With most electrons now locked into atoms, the scattering of photons drops dramatically. The universe transitions from opaque to transparent. Photons last scattered at this epoch stream freely in all directions, largely unimpeded, becoming the relic radiation that fills space today at a temperature only a few degrees above absolute zero. The cosmic microwave background thus represents a surface in time, the last foggy moment before transparency. It is often compared to a baby picture of the universe, showing it as it was when it was only a few 100,000 years old. But beneath this familiar metaphor lies a deeper significance. That surface carries fine-grained information about conditions in the yellow fireball, the density, the composition, the spectrum of fluctuations, and even hints about the processes that might have taken place at energies far higher than those of recombination. The early fireball, far from being a chaotic explosion, exhibits remarkable regularities. On large scales, it is extraordinarily uniform. Small deviations from uniformity are present, but their statistical properties follow simple patterns, nearly scale invariant and Gaussian. This simplicity masks a complex question: why was the observable universe so smooth on scales that, in a naive extrapolation, would not have been in causal contact at early times? Why is its spatial geometry so close to flat? And why does it contain nearly the same density of matter and radiation predicted by a model that begins in such an extreme state? These puzzles gave rise to ideas such as cosmic inflation, a brief period of accelerated expansion in the early universe that would stretch space so rapidly that any initial curvature or inhomogeneity would be ironed out over observable scales. In this view, the fireball phase is not the very beginning but the aftermath of inflation's end, when energy stored in a field-driving accelerated expansion is converted into particles and radiation in a process known as reheating. The details remain under active investigation, but the broad picture is that the familiar hot Big Bang is itself a transition from a prior, more exotic phase. In this layered narrative, the Big Bang ceases to be a single, sharp event. Instead, it becomes a sequence, a pre-hot phase in which inflation or some other mechanism prepares the initial conditions, a reheating stage that floods the universe with radiation and matter, and an ensuing period of cooling and decoupling that sets up the observable relics. Time, as measured from the end of inflation, thus begins its classical march in a universe already endowed with particular properties, smooth on large scales, slightly rippled with quantum origin fluctuations, and primed for the growth of structure. The fireball, then, is not an explosion hurled into emptiness, but a state in which the laws of physics, applied under extreme conditions, begin to carve out a path along which time can be meaningfully tracked. The hot, dense plasma, the acoustic waves, the nucleosynthesis reactions, and the eventual release of light all mark stages in the emergence of a temporal narrative from an initially featureless description. Each milestone in that early evolution is not just an event in time but a step in the process by which time acquires a rich, structured content. When the universe first became transparent, it crossed a threshold that reshaped how its history could be recorded. Before recombination, information was trapped in the incessant scattering of photons. Afterward, light could travel largely unimpeded across intergalactic distances. In that moment, the cosmos produced a nearly perfect record of its own state, encoding temperature and density variations into a field of radiation that would persist for billions of years. The cosmic microwave background is not perfectly uniform. Tiny temperature anisotropies, at the level of 1 part in 100,000, speckle its otherwise smooth surface. These anisotropies correspond to regions where the primordial plasma was slightly denser or less dense than average, slightly hotter or cooler. Acoustic waves, driven by the interplay of gravity and radiation pressure, had sculpted these variations before decoupling. When photons last scattered, they captured a snapshot of these oscillations, freezing them into a pattern that could later be observed. The detailed angular power spectrum of these anisotropies, how variations depend on angular scale, carries a wealth of information. Peaks and troughs correspond to modes of oscillation that were caught at different phases when recombination occurred. Their positions and heights reveal the curvature of space, the relative contributions of matter and radiation, and the presence of components such as dark matter and dark energy. They also reflect the spectrum of primordial fluctuation seeded by processes that may have occurred long before recombination, possibly during inflation or some alternative early phase. In this way, the birth of light as a freely propagating background marked not only a change in the physical state of the universe but a transformation in the way its history could be reconstructed. Photons streaming from the last scattering surface provide a direct, line-of-sight view into the early cosmos. They carry with them a kind of temporal layering. To observe them now is to witness the state of the universe at that particular cosmic time, with intervening processes superimposed in more subtle ways through gravitational lensing and integrated effects. Beyond the microwave background, the release of light set the stage for the first luminous objects. For a long interval after recombination, often called the cosmic dark ages, there were no stars, no galaxies, only neutral hydrogen and helium cooling and slowly collapsing under gravity. During this period, the seeds imprinted in the early plasma continued to grow. Slight overdensities attracted more matter, amplifying the contrast with underdense regions. Eventually, in the densest pockets, gas clouds collapsed and heated until nuclear fusion ignited, birthing the first stars. These first stars were massive, short-lived, and unlike most stars seen today. They flooded their surroundings with ultraviolet radiation, beginning the process of reionizing the neutral intergalactic medium. They forged heavier elements in their cores and in their violent deaths, seeding the universe with the raw materials for future generations of stars and for planets. The light from these early stars and galaxies, though heavily redshifted and absorbed along the way, contributes to a faint background that complements the microwave relic by revealing later chapters in the story of structure formation. The emergence of the first sources of light marks another inflection in the narrative of time. Before stars, the universe's changes were largely invisible except through subtle imprints on the background radiation and the distribution of matter. With the ignition of stars, the cosmos acquired visible beacons that traced its ongoing evolution. Each stellar birth and death, each galaxy merger, each flare from an accreting black hole became a marker in the unfolding of time, adding layers of history to the original framework set by the early fireball. From a temporal perspective, the transition from an opaque plasma to a transparent medium, followed by the rise of luminous structures, is the transition from a universe that barely records its own state to one that writes an increasingly detailed chronicle. Light carries information not only about positions and velocities, but about chemical compositions, temperatures, magnetic fields, and more. Spectra of distant galaxies reveal their ages and star formation histories. Absorption lines from intervening gas clouds sketch the distribution of matter along the line of sight. In this way, timed passage is inscribed into the very properties of the light that crosses the cosmos. Yet even the genre of cosmic record has limits. This can obscure regions, scattering and absorbing light. Higher redshift dims and stretches signals, pushing them into bands where detection becomes challenging. Gravitational lensing can magnify and distort images, complicating the reconstruction of intrinsic properties. Despite these complications, the combined analysis of many lines of evidence allows cosmologists to piece together a consistent timeline, extending from the birth of light as a freely traveling background to the richly structured universe of galaxies and clusters observed today. Viewed from this perspective, the birth of light is also the birth of extended memory. The universe does not possess memory in any conscious sense, but its physical processes imprint traces of earlier states into present configurations. The microwave background, the spectra of ancient stars, the distribution of galaxies, and the content of intergalactic gas all serve as archives. Each archive has its own temporal reach and resolution, and together they form a layered map of cosmic time. In the story of where time was born, these developments represent the early chapters in which time acquires both direction and content. The Big Bang and the Fireball phase establish an era rooted in low entropy and expansion. Recombination and the release of photons establish a global time stamp, a surface from which time can be measured in both directions, toward the past via theoretical extrapolation, and toward the future via the growth of complexity. The first stars and galaxies illuminate the future, filling it with events that can be ordered, counted, and related, turning an abstract parameter into a lived, structured history. The large-scale structure of the universe, the arrangement of galaxies, clusters, filaments, and voids did not arise from a perfectly smooth beginning. It grew from small initial and homogeneities, tiny deviations in density and curvature present in the early universe. Remarkably, the most compelling models suggest that these seeds of structure have a quantum origin. At the deepest level, the history of galaxies and clusters, and thus much of cosmic history, may trace back to ephemeral quantum fluctuations magnified to astronomical scales. In inflationary cosmology, a period of rapid, accelerated expansion precedes or coincides with the earliest moments of the hot Big Bang. During this phase, a field with a high energy density dominates the dynamics, driving exponential growth of the scale factor. Quantum fluctuations in this field, along with fluctuations in the space-time metric, are continually generated. Under normal circumstances, such fluctuations would remain confined to microscopic scales. However, the enormous stretching caused by inflation carries them far beyond the local horizon, effectively freezing their amplitudes as classical perturbations on super-horizon scales. These frozen perturbations become part of the initial conditions for the subsequent hot Big Bang phase. When inflation ends and the universe reheats, the imprinted fluctuations appear as small variations in energy density and curvature. Over time, as the universe expands and matter begins to dominate over radiation, gravity amplifies these variations. Regions with slightly higher density attract additional matter, growing into the seeds of galaxies and clusters. Regions with slightly lower density become the expansive voids between the great filaments. The statistical properties of the observed cosmic microwave background anisotropy strongly support this picture. The nearly scale invariant spectrum of fluctuations, with only a slight tilt, matches the expectations of a broad class of inflationary models. The Gaussian nature of the fluctuations, with only tiny deviations from perfect Gaussianity, also fits well with the idea that they arise from linear quantum processes. In this sense, the pattern of hot and cold spots in the microwave sky is a direct visualization of the quantum seeds from which cosmic history would unfold. The conceptual shift here is subtle but profound. Quantum mechanics, commonly associated with atoms and subatomic particles, appears as a key player in setting up the grand architecture of the cosmos. Randomness at the smallest scale shapes the arrangement of matter across billions of light years. The locations of galaxy clusters and voids, the alignments and patterns in the cosmic web, and even the distribution of environments in which stars and planets form all trace back to a stochastic process in the universe's earliest instance. This quantum origin of structure introduces an element of contingency into cosmic history. While the overall statistical properties of the fluctuations may be determined by fundamental physics, the specific realization, the exact pattern of highs and lows, the particular placement of structures is not. Different possible universes, governed by the same underlying laws, could exhibit different detailed maps of structure. The universe inhabited is one draw from this ensemble, a single realization of a more general pattern. Despite this inherent randomness, the quantum seeds do not undermine the emergence of a meaningful temporal narrative. On the contrary, they provide the diversity of initial conditions required for rich evolution. Without variations in density, the universe would remain a featureless, expanding bath of radiation and matter. There would be no stars, no galaxies, no chemistry beyond the simplest elements, and no observers to contemplate their origins. The subtle irregularities in the early universe, born from quantum processes, are essential ingredients in the story of how time acquires complexity. The role of quantum fluctuations near the beginning also raises questions about determinism and predictability. On large scales, the equations of cosmology are deterministic. Given initial conditions, the subsequent evolution is fixed. Yet the initial conditions themselves, in this picture, emerge from quantum processes that assign probabilities rather than certainties. The ultimate origin of the specific pattern of fluctuations cannot be explained by classical cause and effect alone. This intertwining of determinism and indeterminacy becomes part of the texture of cosmic time. Furthermore, the interplay between quantum mechanics and gravity at these early stages hints at an incomplete understanding. Inflationary models typically treat the inflated field quantum mechanically, but spacetime geometry classically. A full theory of quantum gravity would likely modify this treatment, perhaps altering how fluctuations are generated and how they become classical. The fact that such a semi-classical approach works as well as it does is both a triumph and a clue, suggesting that the deeper theory must reproduce these results in an appropriate limit. In the context of the question of where time was born, quantum seeds represent the first detailed features etched into the canvas of cosmic time. Before their imprint, the universe's description may have been almost featureless, a simple, symmetric state with few distinguishing marks. With their appearance and amplification, time gains layered character. Different regions evolve differently, structures form in diverse sequences, and histories diverge. The cosmic timeline ceases to be a single, uniform trajectory and becomes a branching, textured web of events. The galaxies visible today, the clusters and voids, and the intricate networks that tie them together are, in a sense, fossilized patterns of primordial quantum noise. They are the macroscopic realization of microscopic uncertainty. Time's story, written across the sky and through the distribution of matter, turns out to have begun with whispers of randomness, amplified by gravity into the grand chorus of cosmic structure. As the hot Big Bang model and its refinements grew increasingly successful, a natural question pressed forward. If the universe emerged from a hot, dense early phase, what, if anything, came before? The standard formulation of general relativity, when applied extrapolating backward, delivers a singularity, a boundary where densities and curvatures diverge and the equations themselves fail. This singularity marks the edge of classical spacetime. Beyond it, the theory offers no reliable guidance. One possibility is that this edge represents a true beginning, that time itself does not extend beyond a finite value into the past. In such a scenario, questions about what preceded the Big Bang may simply lack meaning, much as queries about a location north of the North Pole must supply concepts beyond their domain. The hot Big Bang, then, would mark not a transition from a prior state but the inception of space-time and its attendant notions of before and after. Yet theoretical explorations have opened other avenues. In bouncing cosmologies, the universe undergoes phases of contraction and expansion. A contracting phase, dominated perhaps by different forms of matter or energy, leads to a minimum size or maximum density, followed by a bounce into expansion. Quantum gravity effects might regulate the bounce, preventing singularities and extending space-time through the point where classical theory fails. In these models, the hot Big Bang is not an ultimate origin but a turning point in an ongoing story. Other proposals imagine a pre-inflationary or emergent phase in which space-time and its geometry coalesce for more fundamental degrees of freedom. Before the hot, dense state, there could be a regime without a classical notion of space or time, governed by a quantum system whose low energy, large-scale behavior resembles the spacetime familiar from general relativity. The Big Bang, then, appears not as a beginning from nothing but as a phase transition akin to the way a fluid can condense from a gas or a crystal can form from a melt. In some time-symmetric models, the Big Bang-like surface serves as a temporal mirror. Entropy increases in both directions away from this surface, giving rise to two oppositely directed arrows of time. Observers on one side perceive their time as flowing away from the central low entropy state, while hypothetical observers on the other side would experience their own arrow pointing the other way. From a global viewpoint, time would extend indefinitely in both directions, but from any given side, the Big Bang remains a boundary in the observational past. Each of these ideas grapples with the same core issue, the inadequacy of classical spacetime concepts with extremely high energies and curvatures. To ask what came before the Big Bang is to demand an answer from a framework that breaks down near the regime in question. A more complete theory of quantum gravity is expected to reshape this question, perhaps replacing singularities with smooth, albeit exotic, structures or replacing continuous time with something more discrete or relational. Observationally, the possibility of a pre-Big Bang phase is constrained by the lack of clear imprints. Any prior epoch must connect a hot phase in a way that respects the observed uniformity and near flatness of the universe, as well as the specific spectrum of primordial fluctuations. Subtle signatures, unusual correlations in the cosmic microwave background, particular patterns of non-Gaussianity, or relic gravitational waves with distinctive spectra are sought as possible windows into an earlier chapter. So far, no decisive evidence has emerged, leaving the question open but tightly framed. From the standpoint of where time was born, these explorations suggest a nuanced picture. The hot Big Bang clearly marks the beginning of the classical, thermodynamic arrow of time in the observable universe. Before it, if any meaningful sense of before applies, time may have had a very different character or may have been absent in the usual sense altogether. The emergence of a low-entropy, expanding state becomes the critical transition at which the familiar features of time direction, causality, and a cumulative history come into focus. Whether or not there was a time before the Big Bang remains an open question. The answer may depend as much on how time is defined as on the underlying physics. If time is tied to the existence of a classical spacetime manifold and a well-defined entropy gradient, then its domain may begin with the hot phase. If time can be generalized to parameterize evolution in a more abstract quantum state, it might stretch beyond the Big Bang, but in a manner that defies direct representation in familiar terms. In this sense, the edges of before mark not just a boundary in physical history, but a boundary in the applicability of certain conceptual tools. The story of time's birth thus includes an acknowledgement that the language used to describe beginnings may itself break down near the point where it seems most needed. The Big Bang is not only a physical frontier, it is also a frontier of intelligibility. The Planck scale stands as a symbolic curtain between known and unknown physics. At distances near the Planck length and energies near the Planck energy, quantum effects of gravity are expected to become significant, invalidating any description that treats spacetime as a smooth, classical manifold. In the context of the Big Bang, this regime is unavoidable. Extrapolations backward in time lead inevitably to densities and curvatures where the Planck curtain is drawn. Attempts to peer beyond this curtain have given rise to various approaches to quantum gravity. In loop-based formulations, spacetime is composed of discrete quantum area and volume, woven together into spin networks that approximate smooth geometry at large scales. Time in such frameworks may be relational, emerging from the evolution of these networks relative to one another rather than flowing as an independent parameter. Near the Big Bang, a classical singularity can be replaced by a quantum bounce, in which geometry reaches a minimum size and then re-expands, avoiding infinite densities. In string-theoretic pictures, fundamental objects are one-dimensional strings or high-dimensional branes rather than point particles. The vibrational modes of these strings give rise to the particles and forces observed at lower energies. Spacetime emerges as an effective description of the underlying string dynamics, and additional compact dimensions may exist beyond the familiar four. In some scenarios, the Big Bang corresponds to a collision or interaction between branes in a higher dimensional space, with time and three-dimensional space emerging from this event in a form recognizable to observers. Other speculative ideas, such as causal set theory or emergent gravity, reimagine spacetime as a derived concept arising from more primitive building blocks. In causal sets, spacetime is modeled as a discrete collection of events ordered by causal relationships, with geometry inferred from the pattern of these relations. In emergent gravity, gravitational dynamics and space-time geometry arise from the thermodynamic behavior of microscopic degrees of freedom, much as elasticity emerges from the collective behavior of atoms in a solid. Across these diverse approaches, a common theme appears: time is not necessarily fundamental. It may emerge as an approximate concept in regimes where certain conditions hold, such as large numbers of degrees of freedom, coarse graining, or the presence of particular symmetries. Near the Big Bang, where these conditions break down, time may lose its usual meaning. The Planck curtain, then, is not just a barrier of high energy, it is a barrier to the straightforward application of temporal intuition. In some formulations, the fundamental description is timeless, encoded in a master equation or constraint that does not privilege any particular parameter as time. Dynamics arise only when subsystems are considered in relation to one another, with some degrees of freedom serving as effective clocks for others. In such a view, the question of when the universe began becomes a question about how relational configurations of underlying variables came to approximate a classical spacetime with a meaningful arrow of time. The Big Bang, from this perspective, is the regime in which time is woven from fundamentally atemporal threads. The low entropy, expanding state that characterizes the hot phase is not just a curious boundary condition, but a manifestation of how emergent temporal structure organizes itself from deeper, non-temporal rules. The growth of entropy, the direction of causality, and the unfolding of history all reflect how this weaving proceeded as the universe cooled and expanded. Observationally, the Planck regime remains out of direct reach. However, its influence may be hinted at in subtle features of the cosmic microwave background, in possible primordial gravitational waves, or in small deviations from the simplest inflationary predictions. These traces, if detected, would serve as faint patterns woven into the earliest accessible fabric of time, hinting at the loom behind the curtain. In contemplating where time was born, the role of quantum gravity underscores that the origin of time is inseparable from the origin of spacetime itself. Whatever theory ultimately succeeds will not merely describe a new kind of particle or field, it will reframe what it means for events to occur, for one moment to follow another, and for histories to have beginnings. The Planck curtain marks the frontier where such a reframing is unavoidable. Although the earliest instants of the universe remain veiled behind the limitations of current theory and observation, their influence permeates the cosmos. Each region of space, each structure, and each beam of light carries echoes of conditions near the birth of time as it is known. The challenge is to learn how to read those echoes. The cosmic microwave background is the most direct remnant of the early universe, but it is not the only one. The relative abundances of hydrogen, helium, and light elements such as deuterium are fossil records of nuclear processes that occurred within minutes of the hot phase's onset. These abundances remain imprinted in ancient gas clouds and in the atmospheres of old stars. By comparing observations with theoretical predictions of primordial nucleosynthesis, cosmologists confirm not only the occurrence of such a phase, but also its timing and density conditions. The large-scale distribution of galaxies and clusters encodes the growth of structure from the initial fluctuations. Statistical analyses of galaxy surveys reveal patterns that align with the same primordial spectrum inferred from the microwave background. Baryon acoustic oscillations, relics of sound waves, and the early plasma leave subtle imprints in the clustering of galaxies, providing a standard ruler for measuring the expansion history. These features tie the behavior of the universe billions of years after recombination directly back to the physics of the early fireball. High-energy astrophysical phenomena, such as gamma-ray bursts and the jets of active galactic nuclei, probe extreme conditions that, while far gentler than those at the Big Bang, still test the interplay of gravity, radiation, and matter under intense circumstances. The behavior of particles and fields in these environments can constrain models of fundamental physics that also apply to the universe's first moments. In this way, distant explosions and luminous jets become laboratories for theories that aspire to describe the birth of time. Gravitational waves offer another channel of communication. Mergers of black holes and neutron stars emit ripples in spacetime that travel across the cosmos largely unimpeded. Detectors that sense these waves effectively listen to the dynamic side of the universe. In addition to events in the relatively recent cosmic past, there may exist a background of gravitational waves generated by processes in the early universe phase transitions, inflationary fluctuations, or other exotic phenomena. Detecting such a background would provide a new kind of relic, complementing the electromagnetic and particle-based records. Even dark matter and dark energy, though poorly understood, are part of the legacy of the early universe. The abundance and distribution of dark matter influenced structure formation from the earliest times, while dark energy governs the acceleration of expansion in the later universe. Any complete account of the Big Bang and the birth of time must accommodate these components, explaining not only their current effects but their origins and transformations across epochs. On more familiar scales, every atom heavier than helium tells part of the story of cosmic evolution that follows from the early conditions. Carbon, oxygen, iron, and heavier elements are products of nuclear processes in stars and supernova. Their presence in planets, interstellar dust, and living organisms reflects cycles of birth and death that could not have occurred without the initial asymmetry between matter and antimatter, the specific expansion history, and the primordial element mix established shortly after the hot phase began. Thus, the present universe is saturated with evidence of its beginnings. Time's birth is not only recorded in abstract equations and faraway radiation, but is also woven into the matter that composes familiar environments. The air, the rocks, the light of the sun, and the faint glow between galaxies all carry traces of processes that unfolded near the origin of time as it is experienced. Recognizing these connections transforms the question of where time was born from a distant, almost mythic inquiry into a scientific investigation anchored in tangible data. Each observation, whether of a distant galaxy's redshift, a star's chemical composition, or a passing gravitational wave, adds a sentence to a story that stretches back to the earliest moments. The coherence of this story, across multiple lines of evidence, reinforces the notion that the hot Big Bang and its immediate precursors truly mark a foundational transition in the universe's temporal structure. Despite the richness of the evidence and the success of current models, there are intrinsic limits to how far back the universe's history can be reconstructed. Some limitations are practical. Telescopes have finite sensitivity, detectors have noise, and certain signals are attenuated or obscured by intervening matter. Others are more fundamental, arising from the structure of spacetime and the nature of quantum mechanics. The observable universe is bounded by horizons. The particle horizon defines the maximum distance from which light could have reached an observer since the hot phase began. Beyond this horizon, regions may exist that have never been in causal contact with the observer. No amount of waiting or technological advancement can bring information from beyond this boundary. The story of the universe accessible to any given observer is, therefore, a partial one, confined to a finite patch of a potentially much larger whole. Cosmic variance imposes another limit. Certain observables, such as the largest scale anisotropies in the cosmic microwave background, can only be measured in a finite number of instances effectively, in one realization, the sky that exists. Statistical fluctuations on those scales cannot be reduced by observing more systems because there are no additional independent samples. This irreducible uncertainty constrains how precisely certain aspects of the early universe's conditions can be inferred. At a deeper level, quantum uncertainty affects any attempt to specify exact initial states. Even if a complete theory of quantum gravity were in hand, describing the earliest configuration of the universe in exhaustive detail might be neither possible nor meaningful. Quantum states are characterized by probability amplitudes, not definite values, and the observable consequences always carry some degree of indeterminacy. The precise pattern of primordial fluctuations, for example, is one realization drawn from a probability distribution. No deeper deterministic reason may exist for its exact form. Furthermore, processes such as inflation can themselves erase information about prior states. If a period of accelerated expansion stretches space by many orders of magnitude, any pre-existing inhomogeneities or anisotropies may be diluted beyond detectability. Only the fluctuations generated during inflation remain. In such cases, the observable universe carries little to no imprint of what came before inflation, placing a hard limit on reconstructing any earlier history. The presence of singularities or their quantum replacements also complicates the notion of explanation. If the Big Bang is replaced in a more complete theory by a bounce or a transition, that theory will still likely prescribe some boundary conditions or initial configurations for the deeper degrees of freedom. The question of why those particular conditions obtain may remain. In this sense, the search for where time was born may culminate not in a final cause but in a framework within which certain facts are accepted as given, constrained by consistency but not derived from anything deeper. These limitations do not render cosmology futile, rather they define its scope. Within those boundaries, the universe's history can be reconstructed with remarkable detail and confidence. Beyond them, questions persist that may be answered only in more abstract or probabilistic terms, if at all. The horizon of explanation thus becomes part of the story of time's origin. It reminds that not all aspects of the beginning are, whatever will be, accessible to empirical inquiry. The universe, as understood through contemporary cosmology, appears to have emerged from a hot, dense early phase that marks the onset of the classical flow of time. Quantum fluctuations, extreme energies, and novel phases of matter and space-time shaped, within the first instance, the conditions under which galaxies, stars, planets, and life would later arise. The question of where time was born has thus been translated from myth and speculation into structured investigation grounded in measurement and theory. To live now is to inhabit a universe far removed in temperature and density from its beginnings. Yet the passage of time from that origin to the present is encoded everywhere. Every star's age, every galaxy's redshift, every chemical element heavier than helium, every faint ripple in the cosmic microwave background, and all of these are manifestations of processes that unfolded after time's birth in the hot Big Bang and whatever prelude preceded it. The narrative assembled by cosmology does not rely on dialogues or dramatic confrontations. It unfolds in the quiet convergence of data and equations, in the match between predicted spectra and observed lines, in the correlation between patterns on the microwave sky and structures mapped by galaxy surveys. It tells of a universe in which time, as a directed, structured parameter, emerged under specific conditions and then guided the evolution of matter and radiation into the complexity that now contemplates its own origins. Understanding that time itself may have a beginning, or at least a transition from a qualitatively different regime, alters perspective. The sense of continuity that stretches backward through history does not extend indefinitely. Instead, it encounters a horizon beyond which familiar concepts fail. The arrow of time, so deeply woven into memory and anticipation, is revealed as a feature of a particular phase of the universe rather than a universal, unconditioned fact. This realization does not diminish the significance of individual experiences or local histories. On the contrary, it situates them within a grander context. The fleeting lives of stars, the slow dance of galaxies, and the brief existence of sentient beings all occur within the aftermath of time's birth. They are chapters in a book whose opening pages are written in the language of high-energy physics and quantum gravity, and whose later chapters are composed of chemistry, biology, and consciousness. The universe will continue to evolve, and time will continue to be measured, remembered, and anticipated as long as there are systems capable of marking change. Yet the origins of the temporal structure, bound up with the Big Bang and its immediate vicinity, will remain partly hidden behind horizons of knowledge. Within those constraints, cosmology has nonetheless traced a compelling arc from an opaque, hot plasma to a transparent, structured cosmos and, eventually, to observers capable of asking when and where time began. In contemplating the mystery of the Big Bang, one stands not outside the story, but inside it. Every observation, every calculation, and every reflection occurs in the same universe whose origin is under scrutiny. The very capacity to inquire is a product of the processes set in motion when time acquired a direction and a stage on which events could unfold. To seek the birthplace of time is, therefore, to follow a thread that leads back not only through distant galaxies and ancient radiation, but through the conditions that made inquiry itself possible. The mystery is not resolved in a single equation or image. It persists at the edge of theory and observation, at the Planck curtain, at the singular or non-singular surfaces where classical space-time falters. Yet the path toward understanding is clear enough to trace, from expansion to fireball, from birth of light to quantum seeds, from questions about before to speculations about deeper frameworks where time is woven. The universe remembers its birth in the structures and signals it presents, and within those memories lies the closest approach to an answer about where time was born.